Now that we're comfortable with what a logarithm is and how we can use a log, we're going to get into the most important thing for our course with logarithms, and that's how do you solve exponential equations by using a logarithm. To solve exponential equations, we can take the log of any base, but base 10 is the most convenient because it's on our calculator. We can take the log of both sides. We know in equations we can do the same thing to both sides of the equation and it will be still equal. Same exact idea, we can take the log of both sides. And then when we do that, that exponent, where the variable is, can move out front, and now it's a factor instead of an exponent. Small caveat here, and we'll get to this in a little bit, but the part with the exponent must be alone first. So we can only have the 3 to the x in this example by itself. If there was anything else there, we'd have to take care of that before we could solve. So what this means, it sounds kind of complicated, but it's actually really simple. What this means is if we've got the exponent being a variable, or the variable located in an exponent, all I have to do is take the log of both sides of the equation. Because when I take the log of both sides of the equation, we know that an exponent inside the log can move out front. So this becomes x times the log of 3 equals the log of 45. We can solve this really quick. That's x times the log of 3. We want to get the x alone, so we'll divide by the log of 3 on both sides. And then we end up with x is equal to log 45 divided by log 3. Well, that's just a quick function on our calculator. So we pull out our calculators. Remember, because we chose a convenient log base 10, we can actually do this on our calculator really quick. The log of 45 divided by the log of 3, and we get x is equal to approximately 3.465. Before, our only hope of solving exponential equations was to get the same base on both sides. But sometimes that is just impossible. You can't get the same base on both sides. So in that case, we just have to take the log of both sides and then solve for the x. And it comes out quite quickly, especially with the advantage of the calculator. So let's try a couple examples that are a little more involved, but not too difficult either. Again, we see the exponent contains the variable 7 to the 2x minus 1 equals 34. So what we're going to do is we are going to take the log of both sides of the equation. When we do that, the exponent is going to move out front. And to kind of help us here, that exponent needs to move out front as a group. Keep it in parentheses if there's a lot going on in there. 2x minus 1 times the log of 7 equals the log of 34. And then we can solve. First, let's get rid of that log by dividing it out. Divide both sides by the log of 7. And then 2x minus 1 equals the log of 34 divided by the log of 7. Now you can change those logs into numbers at any point. I like to wait until the very end because it's going to guarantee when I type it in my calculator, I have the exact answer and no rounding error. So I'm going to keep that log 34 divided by log 7 as a group, and we're just going to add 1 to both sides, working on getting the x alone. 2x equals log 34 over log 7 plus 1. And then divide both sides by 2. We got to divide the entire thing by 2. So we end up with this weird looking fraction that x is equal to the log of 34 divided by the log of 7 plus 1, all divided by 2. And to make sure I don't get in trouble with my calculator, I need to know if I need parentheses around those logs. Also, my calculator needs to know I want the entire numerator divided by 2. So I need an extra set of parentheses. So lots to type in here, but it's just an exercise in typing it into the calculator. I'm going to open a parentheses first and type in the log of 34. Close the parentheses on the log. Divided by the log of 7. Close the parentheses on the log. Plus 1. Close the parentheses on the numerator and divide by 2, and I get that x is equal to 1.406. Now, I would have had approximately the same answer if I had changed way back at the beginning that log 34 divided by log 7 to a decimal at that point, and it would have still been pretty close to accurate. It doesn't really matter where I make that decision. I just find that it's more accurate if I wait until the end to plug it all in my calculator. This last example here, we've got the variable again located in the exponent, but what you might notice is the exponent part, the 2 to the x, is not alone. It's multiplied by something, and there's something added to it. We cannot do logs until that's taken care of. So first, let's get rid of the minus 1 by adding 1 to both sides. And we get 3 times 2 to the x equals 10. Divide both sides by 3 to get the exponent part alone. And we have 2 to the x equals 10/3. And now, the variable part, the exponent part is alone. Now we're ready to take a log base 10 of both sides. Which is nice because when we do, the exponent moves out front. So we have x log 2 equals the log of 10/3. And we'll just keep that 10/3 in parentheses there. To get the x alone, we just divide both sides by the log of 2. And then x is equal to the fraction, the log of 10/3, divided by the log of 2. So what's that equal? Well, we'll just go to our calculator real fast. And I will type in the log of 10/3, close the parentheses on the log, divided by the log of 2. And x is equal to 1.737, rounding to 3 decimal places. So that's how we can use logarithms to solve exponential equations. Now, I know the question you've always been wondering about logarithms is why are we talking about musical wood in math class? Logarithms? Okay, bad joke. Anyways, we are solving exponential equations with logs. Now we can solve any exponential equation by taking a log base 10 of both sides, solving for the x after that exponent moves out front, and then we are ready to go from there. Take a look at the homework assignment, practice a few of these, and let your instructor know if you have any questions.